All right, so now that you've been exposed to polar functions and you've had a chance to look at how you can do crazy things in Desmos with polar functions, the last thing that I want to show you is I want to show you how you can turn a rectangular function into a polar function, okay? Also, if we get a chance, we'll actually take a polar function and turn it back into a rectangular function, but that actually can be a lot more challenging. We're not going to do anything too crazy. We're going to do a few simple examples because the more complicated the rectangular function is, the more difficult it is to convert it into a polar function. So we're going to limit ourselves to only two examples. We are going to do a linear function and we're going to do a very simple, just the parent quadratic function. And we have to use our conversion factors here because we're dealing with an x and a y and we want to turn them into r and theta. Therefore, we're going to have to use our conversions between rectangular coordinates and polar coordinates. So let's start with something simple. Let's say that we want to convert y equals, let's do a simple linear function. Let's say we're going to convert 3x plus 5. Okay, so we got a linear function, 3x plus 5. We know what this looks like as a graph. If we actually, let me pull up a coordinate plane. I'm going to go get a coordinate plane right now here, and we'll turn it on. All right, and you can see if we were to graph y equals 3x plus 5, we would go to the y-intercept of positive 5, 1, 2, 3, 4, 5, which happens to be in the middle of the 5 here. Sorry about that, right? And then we would do a slope of 3, right? We'd go up 3, 1, 2, 3, somewhere up here and over 1, right? Or we could go down 3 and back 1. And we know that we could then draw a straight line through that. And this would be our graph for 3x plus 5, okay? Well, what I'm telling you is this, is that we can actually create a polar function that when you graph it as a polar function, as r is a function of theta, then if you were to graph it on a polar plane, it would actually give you a straight line, just like 3x plus 5 gives you a straight line. In fact, it would give you the same straight line. And what I'm going to do is, we're going to go ahead and convert this 3x plus 5, then we're going to switch to Desmos, and I'm going to show you that the graph for 3x plus 5 is the same as the polar function that we're going to convert it into. Okay? So it's very simple. What you're going to do is you're simply going to replace the y with r times sine of theta. So we're going to substitute the y with r times sine of theta is equal to 3 times r times cosine of theta. So this is, we know that that's x and this is y. So this is y equals 3x plus 5. And now here's what we need to do. We need to solve for r. We need to isolate r, get r all by itself, and everything else has to be on the other side. So it's going to take a little, kind of some funky algebra that includes a little bit of factoring, okay? So the first thing you want to do here is this, well, really the first thing we did was substitute out x and y. Whoops, x and y, okay? Once x and y have been substituted out with r sine of theta and r cosine of theta, the second thing you're going to do is move all terms with r to the left side and all terms without r to the right side. All terms without r to the right side. Okay? Now, there's only 3 terms. There's r sine of theta. That's one term. There's 3r cosine of theta. And then there's 5, okay? Remember that terms are separated by plus and minuses and equal signs, okay? So we have a term, then an equals, then a term, then a plus, then a term, okay? Well, these two terms both have r's in them. This one does not have an r in it. So this one is going to stay on the right side. This one's going to stay on the left side. But this one, 3r cosine of theta, that has to be moved over to the left side. And the way we move things is with addition and subtraction. This is a positive term, 3r cosine of theta. So we're going to subtract 3r cosine of theta from both sides minus 3r cosine of theta, because you know the rule in algebra is whatever you do to one side, you have to do to the other side. That's going to cancel the 3r cosine of theta on the right, carry down the equal sign, carry down this positive 5. So now all we have over here is a 5. Now over here we have r sine of theta minus 3r cosine of theta. Then the next thing you're going to do is factor out r. Factor out r on the left. All right? So now both of these terms have an r in them, so we just have to factor the r out. So I'm going to divide this by r. I'm going to put an r over here. Divide this by r and divide this by r, which means I have to open up a parentheses. So I'm taking out a common factor. Okay, r is a common factor to this term and this term. I'm dividing it out. Well, r sine of theta divided by r leaves just sine of theta. Minus 3r cosine of theta divided by r. If we divide r out of this, it'll cancel the r, and all we'll have left is 3 cosine of theta. 3 cosine of theta is equal to 5. And then the last thing you're going to do is solve for r. Solve for r. Well, to solve for r, to isolate r, to get it by itself, all I have to do is divide by sine of theta minus 3 cosine of theta. And if I divide by that on the left side, I also have to divide by that on the right side, because it's algebra. Whatever I do to one side, I have to do to the other side. Sine of theta minus 3 cosine of theta. Go. On the left side, that's going to cancel sine of theta minus 3 cosine of theta, and it's going to leave me with just r. So r is equal to, and then this just stays as is, 5 over sine of theta minus 3 cosine of theta. Okay? And so this, what I'm showing you here, is the equation of a line in polar form. Okay? Now, I want to show you something. We're going to, in just a couple minutes, we're going to go look at this in Desmos. But before we look at it in Desmos, I want to show you what this 5 means and what this 3 means. Do you see how up here we know that in linear form, you know, in the slope-intercept form, that this 3 here, that is the m, the slope of the line, right? And this 5, that is the y-intercept, that's the b, mx plus b, right? Well, if we go down here to where we see where the 5 is, the b, we can create a general form here. We can see that the y-intercept is always going to be in the numerator of this formula. So we have a general form of a straight line in polar form. So r is equal to b over, we're always going to have this sine of theta here, sine of theta, minus, and then we're always going to have the m in front of cosine. So remember, cosine of theta is like x, right? So mx, you know, the only thing we're missing is the r, but we move the r over here. Okay, so it's going to be m times cosine of theta. And here's what I'm saying, is that you can take any line, the equation of any line, take the slope and put it down here in front of the cosine, take the y-intercept, put it up here in the numerator, and you will have the polar function that gives you the equation of a line that is the same as the y equals mx plus b form. Okay? So what we're going to do right now is, why don't we just go ahead and go to Desmos, and I'll show you that this line is the same thing as this line. Then what we're going to do is we're going to come back, and I'm going to challenge you to identify the polar form of a whole bunch of lines so that you can get the pattern down. Okay, so let's go ahead and put in the first line. Let's put in y equals 3x plus 5, and we can see that this is a line, right? See, we have a y-intercept at positive 5, right? And we can see that the slope is, if we go up 1, 2, 3, and over 1, so this has a slope of 3. We can also go down 3, 1, 2, 3, and back 1. We can see that this line definitely has a slope of 3 and a y-intercept of 5. Okay? All right, so now what we're going to do is we're going to put in our r is equal to, and I'm going to create a fraction here, so I'm just going to put 1 over 2, but I know that I need to have a 5 in the numerator, and in the denominator I need to have sine of theta, right? And then we have to put in minus, right? And we got to put in a slope of 3, right? So 3 and then cosine of theta. And look at that. It just put something right on top of our other line here. Look, see if I turn off this one, if I take out the black curve, you can see there's the purple curve. That is the 3x plus 5. And if we put this one back in, there is r is equal to 5 over sine of theta minus 3 cosine of theta. And if I zoom out, you can see that it's going for a long time. Okay, it's going. Look here, we're up to like 100 or almost 200. Now we're going to get up to 500, and that x is equal to 500. And it just keeps going out and farther out and farther out and farther out. And so it is definitely the same line. What we're, let's say that I wanted to change this line. Let's say that I wanted to, I'm going to turn off this other line. Let's say that I wanted to do a line that had a y-intercept of -2. I could just change the 5 to a -2, and you can see now it's the same line with a slope of 3 with a y-intercept of -2. Let's say I wanted to change the slope to, or let's make the y-intercept -4. Okay, so here's the y-intercept -4. Let's change the slope to 2. So we'll change this 3 to a 2. And look, now it has a slope of up 2 over 1. Now it has a slope of 2. If I get rid of the number altogether, there will be a 1 there. Now it has a slope of 1 with an intercept of -4. And now if I change this to a plus, if I make it plus 3 instead of -3, you can see that the slope is now -3, down 3 over 1. Okay, and so we can make lines in polar form using this b over sine of theta minus m of cosine of theta, and this is the polar function for a linear graph in using polar coordinates. Okay. All right. So let's go back and we'll practice identifying different linear functions in rectangular coordinates, and then identify them in as polar functions. All right. So now I want you to try and identify some of them for yourself. Here's your formula, and I want you to convert this linear equation into a polar function. Why don't you pause the video and do that right now? All right, well, all we got to do is, we know it's going to be r is equal to, we know that it's a fraction. We know the numerator gets the y-intercept, which is 3. The denominator is always sine of theta minus the slope, but the slope is -4. So if we're going to put, if it's going to be minus -4, that becomes plus 4, right? And then we put on cosine of theta, and this is the linear form as a polar function of the rectangular function -4x plus 3. Okay, let's try another one. All right, so what we're going to do is we're going to take this polar form of a straight line and we're going to turn it into a rectangular form of a straight line. Okay. All right, so now there is an algebraic way you can do it, but I want you to just use the basic formula here and try to identify the slope and the y-intercept. So we need to know what m is and we need to know what b is. Okay. Now, normally we have minus m and over here we have minus 7. So the most important thing you have to know here is that that 7, the slope is not negative 7, it's positive 7. You have to do whatever the opposite is of what you see here. So if you see a minus 7, it becomes a positive 7. If you saw a plus 5, it would become a negative 5 slope, okay? And that's because in our formula here, or in our conversion, it's always a minus m, okay? And then we know that the numerator is our y-intercept, so that's an 11. It's not negative, right? If there was a negative out front here, that negative would fall on the 11, okay? But it's a positive 11, so it's just b is equal to 11. And now we can write y equals mx plus b. Okay, so m is 7, then x plus b, that's plus 11. And so here's the equation of our line, which is y equals 7x plus 11. This line is the same as this line right here. All right, we'll make this one our last one, and then we're going to move on and just quickly do the polar function of the parent function of x squared. Okay. All right, so we know that we need to identify the slope and we need to identify the y-intercept. In this case, the y-intercept is negative 9. Okay. Now the slope is, you might think that it was 2, right? But remember, we have to do the opposite of this plus 2 because over here it's minus m. Okay, so we have to do the opposite of plus 2, which would be negative 2, and therefore our slope is negative 2, our y-intercept is negative 9, and therefore our equation would be y equals m, which is negative 2, x plus b, which is minus 9. And so this now is the equation of the line that is drawn in polar coordinates when we use the polar function that looks like this. Okay? All right, so that's the basic idea. If I were you, I would play around with some of these on Desmos to try and see what kind of cool things you can do with the y-intercept and the slope. And, you know, just change. You can even change whatever's in front of the sign. You can change, you know, you can put a number here, put a number here, change the number up here. Maybe even switch around the sine and the cosine just to see how it affects the polar graph. The more that you play around with this on Desmos, the better you'll understand the polar coordinates, okay? Now let's try the parent graph for x squared. All right, so let's say we have this quadratic. This is called the parent function for quadratics. It's y equals x squared. It's an upward parabola. It passes through 0, 0, and it's symmetrical around the y-axis, okay? This is the most basic, most simple quadratic function. And with this basic parabola, okay? So what we're going to do is we're going to follow this procedure over here. The first thing we're going to do is we're going to substitute out the x, we're going to substitute out the y, and we're going to put in what they're equal to over there. We know that y is the same thing as r times sine of theta is equal to. And then for the x, because it's being squared, we're going to put it inside parentheses. So r cosine of theta is being squared, right? Now I want to show you something interesting here. What we can do is we can distribute this squared. We have two things being multiplied. Because they're being multiplied, we can distribute the square. We can put the square on the cosine and put the square on the r. This is the same thing as r squared times cosine squared of theta. Okay? And now over here we're going to have r times sine of theta. Okay? All right, so now before we move on to step 2, we actually have an opportunity. We have like a step 1.5 that does not always present itself. So I'm not actually going to put it in there. Here's what I want you to see. I want you to notice something. I want you to notice that we only have 2 terms, right? And that both terms have an r in them, right? We already said that a minute ago, okay? So when every single term has something in it, for example, let's say that you had some function that said, you know, 2y is equal to 2x to the third plus 2. If every single term has the same multiplier in it, you can actually divide that thing out of all the terms. You can divide every single term by 2 here, cancel the 2, and then 2 over 2 becomes a 1. Okay? All right? And what you would wind up with is y is equal to x cubed plus 1. Well, in this case, because every term or both terms have an r in them, before we continue, before we move on to step 2, we can actually divide both of these by r, and we can remove one of the r's. So we'll divide out r, that'll cancel over here, and all we have left is sine of theta is equal to, and then here we can divide out one of the r's, r squared divided by r. Well, that just cancels one of the r's. And so what we have now is just r cosine squared of theta, right? And so now step 2 says move all terms with r to the left side and all terms without r to the right side. So all we're doing is just sort of flipping this around. You don't even have to do that step, but I like to have the independent variable, or excuse me, the dependent variable on the left side. So I'm going to put r cosine squared of theta on the left and sine of theta on the right. And now all we have left to do, we don't have to factor out an r on the left because there's only one term. So all we have left to do is solve for r. Well, this is really simple. Look, r times cosine squared of theta is equal to sine of theta. All we have to do is divide by cosine squared on both sides, and r is by itself. Cosine squared of theta. Cancel that, and all we have left now is our solution is r is equal to sine of theta over cosine squared of theta. Now, so now this is basically our formula for a parabola. And what we're going to do in just a minute is we're going to break out, we're going to go over to Desmos, and I'm going to show you how this graph, this parabola at x squared, is identical to this relation right here, r equals sine of theta over cosine squared of theta. But here's something else I want to show you, is that this can actually be converted into other trigonometric functions. Sine over cosine squared is the same thing as sine of theta over cosine times cosine, right? So I'm actually going to break this up into sine over cosine times 1 over cosine, right? And so so if we were to multiply this, sine times 1 is sine of theta, cosine times cosine is cosine squared of theta, right? Well, here's what I want to remind you, is that this is the same thing as tangent of theta, and this is the same thing as secant of theta. And what we find is that our solution winds up being, our parabola is r equals tangent of theta times secant of theta. And so what we'll do is, after we graph this and this, we'll go ahead and graph this, and we will see that they are the same equation. Okay, so let's go ahead and first see what is y equals x squared. And you can see that this is a parabola. You've probably seen x squared many times. Passes through 0, 0. We have the points 1, 1, 2, and 4, because 2 squared is 4. We have negative 1 and 1, negative 2 and 4. So now let's see what happens when we have r is equal to sine of theta divided by cosine squared of theta. And you can see that, blue, this one is blue, is the same. It's sitting right on top of x squared. So if I turn off the blue one, you can see there's the red one. They are right on top of each other. Okay, they are the same function. So now down here, I'm going to put in, let's see what we're going to have here. We're going to do tangent of theta. This one's in green. Tangent of theta times secant of theta is also right on top of there. See that? It's the same exact parabola. So these two polar functions are identical, and they both result in the same parabola as what we have known for a long time, the quadratic parent function x squared. Okay?